Hello, thanks for taking the time to watch this particular video. This lesson will be on how to take an original function and sketch its derivative without knowing what the algebraic version of the function is. And so when we do this, there are a few questions that we want to ask ourselves. A lot of times I've noticed throughout my years of teaching this that students make this more hard than what it has to be. If you focus in on a few key questions, then the graph will pretty much guide you into where it is that you, what it is you need to be drawing. So we're going to start off by just looking at our graph and noticing that here that our graph starts off decreasing, and then it gets to this point here, then it starts to increase, and then it comes here and it starts to decrease again. So whenever we are taking the derivative of a function, what we're trying to do is track the slopes of the tangent lines. And so another way of saying that is we're trying to find out, is the function increasing, decreasing, or constant? And so if we look at these points here, we can tell that this graph is decreasing. So that means that the slopes of the tangent line should be negative right up until we get to about here. Okay, so we should have negative slopes for tangent lines for all these x values up until we get to here. And of course here we have horizontal tangent line. If we keep going from this point, then the graph looks like it's increasing from there, which means that the slopes of the tangent lines are positive. And it keeps on happening until we get to about here, where we have another horizontal tangent line. And then after that, we see that the graph starts to decrease again. Okay? So our first question when wanting to sketch what the derivative of this graph is where do we have the horizontal tangent lines? And so we see that we have them wherever we have a dip or a peak in our graph. And so that gives us a clue as to how we're going to start drawing the graph of the derivative. Okay? Of course, we know that for all these points, the slope of the tangent line is negative. So here we know slope of the tangent line is negative. At this point, the slope of the tangent line is 0. And here, going forward, is going to be positive. So since our graph of the derivative is tracking the slopes of the tangent lines, if the slope of the tangent line is negative, then it has to be drawn below the graph. If the slope of the tangent line is positive, it has to be drawn above the graph for those x values. And if the slope of the tangent line is 0, then it has to be on the x-axis. And that's the first key. So here we're at -1, -2, -3. So -3 for our actual derivative graph, this point will be an x-intercept. And of course here we had negative tangent line slopes, positive tangent line slopes. So that means we have to go from the below the x-axis to above the x-axis. So we know that our graph is going to have to do something like this. Okay? If we look at the next place where we have a dip or a peak, it's here at 1. So at 1, we have another x-intercept for the derivative. And so of course we notice here these points have positive tangent lines, and these points over here on the other side of this point have negative tangent lines. So that means that the graph has to be drawn above the x-axis and then below as we get to this point here. Okay? So we know what's happening around this area for the derivative. We know what's happening around this area for the derivative. The last piece of this is you notice that as these points go up and up and up, if we looked at the slope of the tangent lines, it would increase, 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 and then eventually get to a point to where they stop increasing. Okay? And I'm using my pen to represent the slope of the tangent line. So there's a point to where it stops increasing, and then although the slope of the tangent lines are still positive, they're not getting more positive. So it starts to go like that. Okay? So again, I'll say slope of tangent line is 0. Slope of tangent line is 1. Slope of tangent line is 10. Slope of tangent line is 15. And then it gets to some point where the slope of the tangent line does not increase anymore and then has to go back the other way. Okay? And so here, just estimating that, that point would be about right here for the original graph. And so what we call this point is an inflection point, and we'll learn later that that means a place where the concavity of the graph changes. But for now, all you need to know is this is a point where, in this case, the slopes of the tangent line stop getting more positive. So if we come and sort of map that down, that's going to be little after 0, so we'll say about right here. And so what that represents is here, the slopes of the tangent line stop getting more positive. So here, we know that our graph is not going to be able to get more positive than this. So here is where we sort of cap it off, like that, and we create a peak in the graph. So answering the question of where do we have the horizontal tangent lines at, and knowing how the slopes look before and after that, as well as being able to take an estimate of where we have an inflection point, meaning where the slopes in this case stop getting more positive, then we can sort of surmise what the profile of the graph is going to be. And so for this particular function, its derivative will look something like this.